Hello, everyone. So for this video, we're going to be talking about atomic structure and some of the terms associated with the change in atomic structure, like ions and isotopes. I wanted to start off with just a quick rundown of what we've already talked about in terms of the history and the origin of the model of the atom. And so we started with a theory that atoms are these small, indivisible little pieces, and then started to piece together that there are some charged particles in each atom, and then started to get a better idea of the fact that the positive material is located in the nucleus and that the electrons may be orbited around the outside of the nucleus. And then we really came to this idea that the electrons have these like fixed shells or rings surrounding the nucleus, which leads us ultimately to what we're going to talk about within this unit, which is called the quantum mechanical model, where there's certain energy values associated with the placement of the electrons around that nucleus. All right, but again, just some recap. Atomic number is always referring to the number of positive protons located in the core of that atom. And then mass number is the sum of protons and neutrons in total in the nucleus of one individual atom. Right? So an atom always refers to the basic unit of chemical element. It refers to it having a neutral charge, which means that our proton number and atomic number equal the electron number. An isotope refers to two or more of the same element but have different masses, and they're ultimately referring to stable, naturally occurring atoms. And then an ion is what we use to refer to a charged atom, and that indicates that there's an imbalance of positive protons and negative electrons. Remember, the proton number can't change. If we change the number of protons, we change the element. So really what we're looking at is electrons going into the atom to give it more negative than positive pieces, to give a negative total charge, or electrons leaving the atom so that the number of positive protons is now larger and then giving it a positive overall total charge. So we've got these element symbols, which are found on the periodic table. And the element symbol can be used to derive the entire atomic makeup of one atom. And so in the middle, you've got your element symbol. Here we just got a generic X. The atomic number, which we put in the bottom left corner, is oftentimes referred to as a Z. And the Z value is just the total number of protons positively charged in that nucleus. The mass number is in the top left corner, sometimes referred to as with an A. All right, it's kind of like A to Z. And the mass number is the number of positive protons and neutral neutrons. We always list the mass number over the atomic number because if we needed to figure out quickly how many neutrons are in this nucleus, we could do A minus Z, which subtracts out the number of protons, giving us the neutrons in that atom's nucleus. The only thing that's not in the image here is that if we have an imbalance of protons and electrons, positive or negative, you would put the charge in the top right corner. All right, so when we talk about isotopes, there's two terms that sometimes get intermixed, mass number versus atomic mass. Both sound like they're referring to the same thing, but the mass number is always a whole number. So there's no decimal values associated with it, and that's the whole number of protons and neutrons to one specific isotope. So here in this image off to the right, we've got 107 in like the top left corner, kind of superscripted here for silver. And then we've got an isotope of silver that's got a mass number of 109. Again, these whole number values, right? So both of these are naturally occurring versions of a silver atom, and this one has two additional neutrons, and they both would have the same number of protons. When we talk about atomic mass, this is a weighted average of all of the naturally occurring stable isotopes of an element, and that is always indicated with a decimal. These are the values that are located on your periodic table, on all periodic tables. It's the decimal average mass of all of the isotopes of that one element. Okay? And then the other value that's associated with atomic mass is called the percent abundance, and that's just the experimentally determined percentage of that isotope that occurs in nature. All right, so here in this example, we've got 51.86% of all silver has a mass number of 107, and the remaining 100%, or 48.14, has a mass number of 109. So on average, we've got a pretty equal shot of pulling out, if we were to have 100 silver atoms, and I reached into a bag, it's kind of almost 50-50 that the mass might be 107 or the mass might be 109, although there's a slight advantage to the 107 because it's 51.86. So when we think about calculating the average atomic mass of all of these silver isotopes, we have to remember that because we've got almost equal amounts of each, our average mass is going to occur somewhere in between 107 and 109 pretty evenly, and that our average has to land between 107 and 109 because we're taking an average of all of these masses. Right? So the calculation that we would perform is to take the percent abundance, multiply it by the mass number, and do that for each isotope with each percent abundance, right? And then since a percentage is factoring in out of 100 atoms of silver, we ultimately want to divide everything by 100 so that we get the average mass for just one of those atoms. And this calculation here is going to give us 107.96. So again, it's really close to 108, which is halfway in between 107 and 109, but it's slightly less than and slightly closer to 107 than to 109 because we had a greater percentage of mass number 107. All right, so the last thing I wanted to talk about is the electron arrangement of these atoms. So we're going to focus on just the first 18 first. So these are the first 3 periods on the periodic table. And these images are what's referred to as the Bohr models of the elements. So hydrogen is in period 1. It's only got one energy level or one shell of electrons. Lithium through neon are in period 2, and we notice that these each have 2 rings. And sodium through argon are in period 3, and they each have 3 rings or 3 shells. So there's a pretty significant pattern there in terms of the electron arrangement for each atom. And then in the outermost shell, here in group 1, each of those have only one electron in that outermost shell. And if we jump over here to fluorine, which is in group 7, in its outermost shell, there's 1, 2, 3, 4, 5, 6, 7. And in chlorine's outermost shell, there's 1, 2, 3, 4, 5, 6, 7. All right, so that's not, again, a coincidence. That's by design. So where the element lands on the periodic table, we can use that to visualize where its electrons are located, right? The other thing you notice is that for each of these, for period 2 and period 3, the innermost, like first and second shell of electrons are completely filled to their capacity. And we know what those capacities are by looking at the noble gas arrangement of the period before. So neon is completely filled up. It ends the period. And so it's got 2 in the first and 8 in the second shell. So for sodium through argon, those inner 2 shells each have 2 in the first ring, 8 in the second ring. All right, so when we talk about ions, we're going to have to keep in mind that visual model of the Bohr atom. And ions form, again, when atoms gain or lose electrons. So if an atom gains an electron, then it becomes negatively charged because it has more negative components. And if an atom loses electrons, then it becomes positively charged because it has the same number of protons when it was an atom, but it lost some of its negative material, so it's now imbalanced and more positive. There's 2 terms that are associated with this. So any ion that is negatively charged, we refer to it as an anion. And that has to do with, like in a battery, your negative end of your terminal is called the anode, so anion. And then the opposite of that, the positive terminal, is referred to as the cathode, and so we call that a cation. Now, this is probably the best piece of information that I get to share with all my students every year. The easy way to remember that a cation refers to a positively charged ion is that if you pronounce positive as positive, then every positive ion is going to be referring to a cation. And of course, it's the cutest ion ever. Here it's a little positively charged cation. Anyway, let's talk about how these are actually forming. And so we use what's called an ionization equation, and we focus just on the valence electrons. Those are referring to the electrons in this outermost shell. So for fluorine as an atom, here it doesn't have any charge. It's got 1, 2, 3, 4, 5, 6, 7 electrons in its outermost shell, and it's trying to fill that up and resemble neon's outermost shell. So all atoms are trying to get to this completely filled electron arrangement because that's the most stable unreactive arrangement. So what fluorine wants to do is add an electron in here to complete its outermost shell to get 8. So we'll say a fluorine atom plus an electron now is going to give fluorine a negative charge. And we see that same pattern happen with chlorine. It's got 1, 2, 3, 4, 5, 6, 7 electrons in its outermost shell because it's in group 7. And so it wants to add in 1 electron to become a negative 1 charge. So for a cation formation, it's a similar process where the atom is trying to match its electron arrangement to the closest noble gas. But for lithium, which is in period 2, the closest noble gas arrangement is not neon. It's not going to gain 7 electrons to fill that outermost shell. It's ultimately going to eliminate this 1 valence electron, and its first shell is exactly the same as the noble gas in the period before. So all metals in group 1 want to get rid of this 1 valence electron. So down here for sodium, it gets rid of its 1 outermost electron, and what it's left with is these 2 shells, which have the exact same arrangement as the noble gas in the period before, neon. So the way that we draw that in an ionization equation is to always start with the atom, because we're trying to illustrate the atom becoming something charged as an ion. And in order for this lithium to turn into a positive 1 charge, we have to pull an electron out. So we say that this plus the electron that was removed in total is back to where it started. So it starts here with 3 protons, 3 electrons. Here it gets rid of an electron, and we just illustrate that electron as being added kind of outside the structure of this ion. I know it seems kind of backwards, but if you think about the reverse of that, if a lithium ion were to gain an electron, a +1 charge and a -1 charge would balance out the total charges, and it would go back to a neutral lithium atom. All right, so we see the same thing with sodium here. Sodium wants to get rid of its 1 electron, so now it has a +1 charge. So in this table here, we've got a lot of common charges for metals and nonmetals in the periodic table. And you notice that there are a lot of elements that are missing. This is something that we're going to talk about a little bit later. These are our transition metals, and this is where like our nonmetals have metals underneath the group. So our staircase is kind of being omitted here as well. But there are some common trends that occur where all group 1 elements, which only have 1 valence electron, always like to donate that electron to become a +1 charge. So everything that lands in group 1 is still an atom, but when it becomes an ion, it always becomes a +1 ion. Same for group 2, it gets rid of 2 valence electrons, so it wants to become an ion always with a +2 charge. And then over here in group 7, we have our -1 charges. Group 6, which are 2 electrons away from the closest noble gas, want to gain 2 electrons. And then some of the group 5s, which are 3 electrons away from a noble gas, want to gain 3 electrons to match up to that closest noble gas.